Chapter 8 in class exercise 1, problem 8.8. The block brake consists of a pin connected lever and friction block at B. The coefficient of static friction between the wheel and the lever is 0.3 and torque of 5 Newton meter is applied to the wheel. Determine if the brake can hold the wheel stationary when the force applied to the lever is 30 Newton and 70 Newton respectively. So basically what's happening here is that this wheel is subjected to this external torque, 5 Newton meter. And in order to stop this wheel, force P is applied at the lever, and the value of force P is either 30 Newton or 70 Newton, and we would like to know that will this 30 or 70 Newton prevent the block from turning? Will it hold the wheel stationary when the force is applied? So what we will do here is we will actually calculate the required force P to stop the wheel from moving, and that value of P we will compare with 30 Newton and 70 Newton. If let's say for example if the required value is 50 Newton, and then if we apply 30 Newton, then 30 Newton, we need at least 50 Newton to prevent the wheel from turning. So if we apply 30, it will not stop the wheel and it will keep turning at slow speed. But if we apply 70 Newton, which is more than the required 50 Newton to stop or to prevent the wheels from turning, then it will not move. Yeah, so instead of considering 30 and 70, we will actually calculate the required P based on these given numbers and the geometry, and then we will compare any force value with that number. So that's our threshold. If the force applied is more than that threshold, then yes, it will hold the wheel stationary, otherwise it will not. Now there are two physical components here, the wheel itself and the lever. So we need to draw two free body diagrams separately for each one of them. I have shown them separate here. So this is wheel and this is lever. So let's first draw the free body diagram for wheel only. So even though the lever is shown here because I have just used the same image, don't focus on the lever for now, just focus only on the wheel. So for the wheel, the moment applied is 5 Newton meter at point O, which is the pin. So point O has horizontal and vertical support reaction, OX and OY. I have assumed the direction, and that doesn't matter for this problem because I will write the equation of moment about O, so my assumed direction is not that important. Then the wheel in contact with this block B travels in the right direction. So when it turns counterclockwise, the motion of the wheel at the block is going from left to right. So friction acts in the opposite direction, right to left. And since the applied, and we are assuming that the force applied is just right enough to prevent the wheel from turning, so at that time the friction is maximum, so we can assume that F is equal to mu s times n. And then there is normal force coming from the block in the upward direction. So these are the forces experienced by the wheel. Now when it comes to block, the forces are exactly same magnitude but opposite direction. So later when we draw free body diagram for block, then we will show the friction, this is the actually motion, this is friction here for the wheel, and the normal force, and for the block the friction will go here and normal force will act down. Okay, it's Newton's third law of motion, equal and opposite reaction. So then only the system is in equilibrium. Okay, so when we do this, the unknowns are n and fb, so we can apply this as well as ox and oy, but if we write the equation sum of moments about O is equal to 0 when counterclockwise moment is positive, then we don't have to worry about OX and OY because they will not result in any moment about O. So at that time the only moments are phi, which is positive because it's counterclockwise, minus because of friction, so it's FB times the distance, which is 150 millimeters, so we will write that as 150 divided by 1000 meters, so it's 0.15 meters equal to 0. So from that we can solve for the value of FB, which is 33.33 Newton. That's the first step. What about the moment of normal force about O? Again it is 0 because the line of action of the normal force passes through O, so that results in 0 momentum outgo. And then we can apply the friction equation, because for this problem we are assuming that the friction is maximum static friction. So from that we can calculate the value of normal force at B. Now I'm using like this nomenclature B here to indicate that it's at this point B. So NB is FB divided by mu S, which is 33.33 divided by mu is given as 0.3. So this is 111.11 Newton. That's the value of normal force. Now these are the normal and friction forces experienced by the wheel. Now when it comes to lever, those are the same magnitude but in opposite direction. So let's draw the diagram for lever. So for lever, the normal force is acting down, which is 111.11, and friction is acting right, which is 33.33 Newton. That's what we have calculated in the previous step. So once again, this is the FBD at lever. So FBD at lever. Now, since the lever is connected to pin A, there are support reactions AX and AY coming from like the support at pin A. So the question here is, now how many unknowns do we have here? So we have AX, AY, and P. That's our unknown. Remember, we are actually calculating for P. Now, in order to eliminate AX and AY, we can write the sum of moments equation at A. So sum of moments at A is equal to 0 when the system is in equilibrium. Okay, so the only forces that we need to include are this moment force about A, which is 111 multiplied by 111.11 multiplied by 0.2, and that's clockwise, so it's negative. Friction multiplied by this distance from line of action of friction to A, which is 0.05 meters, and that's positive, so it's 33.33 multiplied by 0.05. And then this P, applied force P, so it's P multiplied by this distance total 600 millimeter, which is 6.6 meters. 0.6 is equal to 0. So the only unknown here is applied force P, so we can solve for P, and that's 34.26 newtons. So what it means that when external moment of 5 Newton meter is applied at the wheel, the lever should apply at least 34.26 Newton of force to prevent it from turning. So when the force applied is 30 Newton, it will not stop, or it will not hold the wheel stationary. But when the force applied is 70 Newton, it will hold the wheel stationary. Okay, so that's the final answer. So we can write that answers in the words that, yeah, if P is 30 kilonewton, then it won't prevent the wheel from turning, but when P is 70 Newton, then it will prevent the wheel from turning. Okay, and that's our approach. So how we solve the problem? We have drawn separate free body diagrams for the wheel and lever, and then calculated normal and friction forces at the wheel, and then same normal and friction forces applied at the lever, but they are in opposite direction. So see, this direction and this, they are opposite. This up, this down, they are opposite, but same magnitude. Okay, it's Newton's third law of motion. Thank you.